Hi everyone. Let me check all my settings here. All right, looks good. Okay, so today we're reviewing for the test on Friday, and I've finished it. I haven't got it up online yet, but I finished it. It's 28 questions long. I'll be testing it out this afternoon, go over it myself to make sure that it's not too long. I don't think it is, but that's the only reason I might change the number of questions. It's 28 questions long. And what's on it? Well, the stuff on Newton's laws, solving problems with Newton's laws, which is what we're going to do today. You will also have to know the statements of Newton's laws, just like on that assignment on Newton's laws. You know how I had things like if there's no net force, what happens? Those kinds of questions. So you do have to know Newton's laws. You have to understand them so that you can answer qualitative questions about them, but also solve problems like the one we're going to do today. There's a brief, we did that brief section on Newton's universal gravitational law, Kepler's law, and solve some problems with the third law. Okay, that was that little small, I think it was a 6 question assignment. That's on there. And then the energy stuff. Okay, so I'm going to do Newton's laws today. And I'm going to do a question on universal gravitational law and Kepler's law next time, and also energy next time. Okay, that next time being on Wednesday, and then Friday is your test. The test is going to be the same structure as last time. Basically, I'll open it up beforehand. If you have a conflict, I'm going to give you. So it's one. I'm timing it for 1 hour, which means I expect you to be able to do this in 1 hour. I have techniques for figuring out how long it usually takes students to do a test. I expect you to be able to do it in an hour. I'm going to give you 2 hours though, so you feel relaxed, and also in case there are technical issues, so that I don't know, for some reason you have a technical issue, you don't start to freak out that you're losing time on it. And but if there's a conflict, with something else, let me know. I can always start it up earlier. No matter when you start the test, you will have a full 2 hours to complete it. Okay, and maybe I'll say a little bit more on Wednesday in case I have to tweak the number of questions, but I think it's pretty good right now with 28 questions. Okay, so let's just start. I have a question here, and actually I didn't even write out the full English. I said, you know what, let me just show you a picture, and we'll go from there. Okay, so here's the problem that we're gonna be solving right now. And it's basically a double incline plane. Okay, now we didn't do one of these. We did like an half incline plane, and then a mass dangling off of the end. But it's not really that much of a difference to do a double incline, so I thought I'd do a double incline. It's also a little bit more like the Atwood's machine, which is one of the experiments that you're going to do in the lab. And so there's the setup. I didn't write English for it. Normally I do, rather than give you a picture, but basically you have a 7 kilogram mass on this one side here, which is at 40 degrees, and a 10 kilogram on this other side, which is at 30 degrees. Okay, so what do I want you to work out? I said, well, what's the acceleration of the system, and in what direction is there? And assume there's no friction. Okay, and then questions 2 and 3, I'm going to add static friction first, and then kinetic friction, and that'll be it for today. Okay, so what's the acceleration, and in what direction? Assume no friction. I've got the answers there, but let's jump back to the other whiteboard here and take a look. And to be honest, when there's no friction, you really don't have to worry about the perpendicular forces. I'll draw them in there because you should be complete. And I didn't quite do it this way, when I first showed you this, because I wanted to show you all the steps, and you will need to get the perpendicular gravitational force and normal force when we do parts 2 and 3. But for the first part, you actually don't need them. So let me just show you what's going on here. For gravity, what do we always do? Well, now there's two here, so we'll do one at a time. So there's a perpendicular gravitational force there, and this is mg, and this is the cosine. I'm just going to write the cosine here like that, just to remind you. The perpendicular component is the cosine, the parallel component is the sine, okay? Like that, all right? And that's gravity for that one, all right? So that's not the full formula there. It would be mg cosine theta, actually m1g cosine theta here, and m1g sine theta there. It's just hard for me to draw in this environment, but that's really what you need to remember here, because this is the typical confusion that I've seen happen. And it might have even happened to you during the assignment, where you'll confuse the sine and cosine. Just remember that, and I went through the geometry in the pre-recorded lecture, but just remember that the cosine is the one that's perpendicular to the plane and the sine is parallel. Same thing over here, okay? So you've got gravity this way, whoops, perpendicular component this way, and parallel component that way, okay? Now both of them together are gravity. It's not like one is gravity and the other is like, they're broken up into parallel and perpendicular, because this way you can solve the problem. Now for the normal force, you've got a normal force this way over here. We'll call this one Fn1, because there are two masses, so the normal forces are different. And Fn2 here. All right, but you know where this is going to go when we go to calculate the total force here. Oh, there's a tension. I'm sorry, I forgot the tension. There's a tension up this way, Ft, and then there's a tension this way, and it's the same Ft, and that's because of Newton's third law. Okay, so I'm sorry, I was jumping a bit ahead, but you know where this is going to go. This is going to cancel that one, and this one is going to cancel that one. So really, you don't need the perpendicular, at least for the first question, you don't need the perpendicular component of gravity, and you don't need the normal forces F1, Fn1 and Fn2 here, okay? So all you really need are the parallel components of gravity, all right? Just keep that in mind for now, all right? I'm going to get rid of those x's because we are going to need them in a minute. But for now, we don't need those. Okay, so let me switch back here. All right, so they'll cancel. They'll cancel. So Fn1 will cancel the perpendicular component, it's gone, and Fn2 will cancel that perpendicular component, it's gone. So all you really need is for M1 here. All right, we'll just do it this way. M1 here. This is the parallel component. I should probably label it here. Parallel G. Okay, and like that. Now there's also a tension there, but what we want to do now is we want to form the net force. So this is the net force for number one, okay? And again, you don't know what direction this is going to accelerate in. Maybe I should switch back very briefly here. Like, let me just quickly put in that 2 there like that. Yeah, these are going to cancel. Now, that's going to cancel that, and that'll cancel that, okay? But, there's tension here, just parallel to the plane, and it's going to compete with gravity down, and there's tension here, and it's going to compete with gravity down. You say, well, which one's going to win? We don't know, okay? We don't know at this point. And so let me just draw an acceleration this way. And I think that is actually the direction it's going to go in. But it doesn't matter. If it turns out that you do it the other way, then it'll just come out to be negative, okay? So right now, let's assume that the acceleration is down, the 10 kilogram goes down this way, and 7 kilogram goes up that way. Well then, when you go to calculate the net force here, you say, well, this is going to compete against that. Which one's going to win? Well, Ft has to win, okay? Let me get rid of that, and switch back. So over here, when you do the net force here, you say, okay, well then Ft, the tension, is going to call it F capital T, I guess. That's going to, compete against the gravitational force like that to give you a net force. All right, that's going to give you the net force. Now you don't know Ft, so you can't go any further. Okay, you do know the parallel gravitational force. We calculated that. But now, why did we get F net? Like, why is F net this important thing? Well, there's the second law. Once you've got F net, even if it's incomplete. By incomplete, I mean you don't have Ft there. You know that that's going to equal mg. So that's going to equal ma. That's going to equal m1a, like that. And we know m1, that's 7, because m1 is, I didn't have it written here. I guess I can write it right there. Is 7 kilograms. Okay, so we have m1. And so we can put that in there, and then we get this equation here. Ft minus 45 is going to equal 7 times A. Okay, and you can't go any further. So when you have two masses, this is the situation you get into when you do the free body diagram for one of them. You just get one equation, but you have two unknowns, and so you can't go any further. All right, so let me see if there's any questions in the chat. Let's see, 5 people are watching. Well, that's okay. All right, let's do now the same kind of analysis for M2, like that, and switch back very quickly. So now take a look at what's going on with M2. Once again, you know, Ft is going to compete with the parallel gravitational force, but which one's got to win? Well, remember, the second law not only gives you F net is equal to ma, but it also says that the net force is in the same direction as the acceleration. So the net force, I mean, I didn't do it quite this way last time, but, you know, that net force, that's got to be in this direction too. All right, both A and F net have to be in the same direction. So the gravitational force here, so the parallel component of the gravitational force has to be at Ft. It's going to be bigger. This one's going to be bigger right there. Okay, so knowing that over here, we can write, okay, well, you know, the parallel component is just m2g sine theta. I mentioned that already. Turns out to be 50. Okay, there's the parallel component. Whoops. Like that. And again, no need for the perpendicular yet, but we have now that F net, I'm just gonna, well, I guess I shouldn't cut and paste that because it's quite different. But F net, this is going to be F net for number 2, and that's going to equal, it's the opposite of this one. It's not going to be Ft minus that, because it's going to be the gravitational force that's going to win, the 50 newtons, minus Ft, okay? And that's got to equal m2a, like that. All right, and now we can simplify this piece here. And why? Well, the highlighted piece there, that's again Newton's second law. All right, so Newton's second law not only gives you that F net is equal to ma, it also gives you the direction. All right, and so get rid of the unit there, and this is 10, and there you go. You got your second equation. All right. Okay, so now what? Well, the rest is math in a sense, because you've got this equation here. So now solve for A and Ft in 1 and 2. All right, so we've got, there's equation number 1, and there's equation number 2. We'll put the two underneath one another, like that. And you'll notice that if I add the left-hand side here to the left-hand side there, and I add the right-hand side here to the right-hand side here, the equality is still preserved. So let me do that. I've got this plus that. All right, and that's got to equal this plus that. Okay. And you'll notice that the Ft cancels out, so I could do this on the next line here. That Ft is going to cancel that Ft. All right, and then 7 plus 10 is 17. So this is going to equal 17, like that. And negative 45 plus 50, well, that's obviously 5. So you get that 5 is equal to 17a, and that tells you that a is equal to, let me quickly work that out. 17 divided by 5, 3.4. 3.4 meters per second squared. It came out positive, so the 10 kilogram slides downhill, and obviously the 7 kilogram slides uphill, like that. All right, so I guess I could show you just very quickly what would have happened if you had this backwards. So I'll erase this in just a second. Suppose that for some reason you accidentally chose the opposite direction. Let me show you in the diagram here. Suppose that, like, you weren't thinking, and you, well, not that you weren't thinking, your intuition fails you because like it might have been hard to say, oh, does the 7 kilogram slide downhill or the 10 uphill? Well, then, you would have chosen A in the opposite direction and A in the opposite direction here. Then what would have happened in these equations here is you wouldn't have had 45, sorry, ft minus 45. You would have had 45 minus ft is equal to A, because your F net would have been in the opposite direction. And then instead of 50 minus Ft, you would have had Ft minus 50. And then when you would have added these, you would have gotten -5 on this side. Again, the Ft's would have canceled, and you would have had 45 minus 50, and that would have equaled 17A. And then when you go to solve for A, you would have gotten negative 3.4. And then you would have said, oh, well, then obviously the acceleration has to be in the opposite direction. Okay, so I mean, I didn't show you this before, but just to show you that you don't have to be completely right at this point what direction the acceleration is in. As long as you get it, go consistently, then you'll find that if you get a negative here, then you chose the wrong direction for A. All right, so that almost answers number 1. Okay, it almost answers it. I also said, well, in one direction, I also said, oh, I didn't say it, but I will now. Find Ft. We didn't do this before, find the tension, but it's pretty easy to find the tension. Let's see, also. Okay, it's pretty easy to find the tension, and that is because once you've got A, the acceleration there, you can substitute, so to find Ft, sub for A in 1 or 2. You could choose either one of them, whichever you prefer, and you could substitute into it for A, and then you'll get the answer for Ft. Okay, so you know what? I'm wondering if I'm going too fast. Hopefully I'm not going too fast, guys, for you. I mean, I know you can watch this later, but I try to go at a pace where I don't waste your time, but also I don't go too fast that you can't take notes. All right, so just don't be afraid to say in the chat, "Hey, slow down," or "Can I see that again?" I mean, that's kind of the point of these live streams. So let's pick equation number 1 here, like that. Okay, so in equation number 1, you say, all right, well, I have A now. A is 3.4, like that. All right, and so what's that work out to? So we get that this, oh, there we go. So once you substitute in for A, 7 times A is 23.8, and that tells you that Ft has got to equal, add 45, it's got to equal 68.8, like that. Okay, we could have used equation number 2. If you'd used equation number 2, I mean, let's do that. Just to, this is overkill. So this is using 1. All right. It's a check to make sure that if you want to make sure that you did it right, they have to be consistent. So if we use equation number 2 here, like that, okay, well, then you're going to get that Ft is going to equal 50 plus 10 times A. So what did I do there? Whoops. Did I make a mistake, guys? I wonder if I made a mistake here. So Ft, move that to the other side. No, I did. It's okay. It's okay. So no, I did. That's a minus, isn't it? Oh, darn. And now my editor is gone. I can't seem to edit. Oh, geez, I'm having technical difficulties here. Yeah, exactly. I should have gotten 0.29. Yeah, I know. Thank you. Thank you, guys. Yeah, I see the error. I saw it as soon as I tried to fix but now, let me see. Aha! Thank you. All right, so over here, I'm not going too fast for you guys, but I'm apparently going too fast for myself. Thank you. It's 0.29. And now over here, 0.29. Okay. And yeah, I divided the other way around. All right, you know what? I need coffee. There we go. Brain juice. Now this is going to be um, 45 plus 7 times 0.29. And that's going to be this number here. And now it's going to work out. Okay, because then I'm going to get equal to 50 times minus 10 times 0.29. And yeah, sure enough, it works out, doesn't it? Okay, so let me just make 100% sure. Put that into my calculator here. And a little bit of a round off error, but that's not surprising at all. Okay, so yeah, that's wrong. That's wrong right there. That's 47.03 newtons. Okay, so there was a bit of a round off error, but that's expected. I'm not going to trace it down right now, but thank you very much for noticing that. I kind of noticed that as I was doing this, but you know, like this is kind of one of the reasons why you try to answer something in a redundant fashion is that you'll notice when you make a mistake. Okay, so obviously I divided the wrong way here. I got the reciprocal of it, and as a result, you know, when I got to this point, I go, something is wrong, and then you know, I was able to solve it. I also ran into a weird technical issue that I've never run into before. I lost the cursor. I couldn't seem to get the cursor, but I got it back. Okay, so let me look in the chat here. Yeah, all right. Thanks again, guys. I'm glad someone's awake this morning. All right. So there we go. We've answered our first question. Okay. And the second question now is assume that only the 7 kilogram mass has static friction. Okay. So because this is one of these strange, I don't know, strange, it's like a double incline plane. If I put static friction on both of them, it could turn into a very difficult problem. So I'm going to say, you know what? I'm only going to have static friction underneath the 7 kilogram. Okay. And how much static friction is required and in what direction, and what is the coefficient of static friction. Okay, so let's go back to our diagram here, and it's a little bit messy, so what I'm going to do is I'm just going to undo some of the stuff that I drew here. Okay, good. There we go. Let me see, is this showing up good? It is. All right. So now what? Well, okay. So we know from our previous analysis that this thing really wants to move in that direction there. In fact, if there's no friction, it will move in that direction there. And so you say, okay, so what direction must the static friction be in? And I'm not going to have static friction on this one. Okay, if I had static friction on both of them, like I said, it could be a very difficult problem. So I'm not going to have static friction on here. I'm going to on M2. I'm only going to have static friction on M1. And so which way is it going to be? Well, M1 wants to accelerate uphill. Okay, and so the static friction has to be downhill like that. Okay, and we'll call that Fs. There we go. Okay, Fs like that. So that determines the direction. And now, how big does it have to be? Well, we know now how big these forces are. Let me just write in here. Well, we don't know the perpendicular, so I got to work those out. But let me just write in here what the parallel are. So from above, okay, I won't switch back, but from above, the parallel for the 7 kilogram was 50, and for the 10 kilogram was 50. Okay, so this one here is 50 newtons this way. Okay. And this one here was 45 newtons that way. All right. This is another way that you could see, like ignore Fn1 and the perpendicular component on both of them. Okay. You could see that this one's 45 and this is 50. That's another way to see that A is going to be in the direction that I've drawn it there. Okay. So we've got those two. All right. So now you say, well, can we work out what all the other forces are? On the basis of just those numbers. Well, not the perpendicular. We'll do those on the other whiteboard. But we do have Ft now. And the reason we have Ft is because A is equal to 0. There's no acceleration, static, right? So there's no acceleration. So this force must equal that force. Okay? Because why? Well, if one of them wins, then you're in this situation that we were in a minute ago where you've got acceleration. Okay? There's no acceleration. And so we know that Ft here is 50. All right, and that's from Newton's second law because the forces have to balance if there's no motion. Acceleration is zero there too, by the way, of course. Okay, now Newton's third law says, well, this Ft is the same as that Ft, so guess what? This one is equal to 50. Okay, and that means that these two forces together must equal 50. All right, think about it. We have 50 going up and we need 50 going down. Well, gravity is going to provide 45, so where are you going to get the other 5? You're going to get the other 5 from this one right here. And so Fs has to be 5 newtons. All right. So thinking about static friction is different than kinetic. We'll do kinetic. That'll be the last one we do. But for static friction, you say, well, there's no formula for it. Like, don't use the mu_s formula to calculate the static friction because it's an inequality. It just sets a limit. All right. But what you do is you simply say, okay, Fs simply has to be whatever is needed such that it doesn't move. Well, we've got 45, so we need another 5 in order for it to not move, and that's what the static friction has to be. Whoops, I guess I'll leave that in there. Okay, like that. So switching back here, we can say that how much static friction is there? Well, let's put that down there. Fs has to equal 5 newtons in order for A to equal 0. All right? So that answers this one. How much static friction is there? And in what direction? You saw that from the diagram. It's downhill at the 7 kilogram mass. Okay? All right, so that answers those two. Now, for the coefficient of static friction, like what is it? I actually can't give you the value. All I can do is give you a range. Okay, so what is it? Is probably a better way to say this is what is the range for the coefficient of static friction, because it's an inequality. Okay, and the formula there is, let me see, I have a mu right there. Cut and paste that. Mu_s has to be bigger than or equal to, all right, has to be bigger than or equal to Fs divided by Fn, like that. Okay? Now, which Fn? Well, it's actually Fn1. There's two Fn's, which is why in the diagram here, let me switch back very quickly to the diagram. That's why here I call this one Fn1. It's the normal force for M1, and this one's Fn2. All right? So it's actually Fn1 because only the 7 kilogram has static friction on it. Now, we don't have Fn1, do we? Okay, and so you say, well, all right, let's calculate Fn1. And going back to the diagram here, Fn1 has to equal the perpendicular component of gravity. All right, why? Well, because it's not accelerating perpendicular. Okay, so Fn1 has to equal that m1g cosine theta. All right, and if you take a look here, I calculated Fn1. I already said Fn1 has to equal m1g cosine theta, and that turns out to be this. This one here we don't need. I mean, I wrote it there, but I probably should just remove it from there because we don't need it there. We'll need it down here, okay? But we don't need it there. All right. So, the perpendicular component is cosine. We're only talking about m1, the 7 kilogram one. Okay. And so the perpendicular component of gravity, m1g cosine theta, turns out to be 53.6. Fn has to counter that, so it must also equal 53.6. Okay. And so this here is going to give us a range on the mu_s, okay? And so that's going to equal, well, we know that Fs is 5 newtons, and we know that the Fn1, okay, the normal force is going to be that, and whoops, over here, that's going to turn out to be, and let's see if I do it right this time. 5 divided by 53.6. And it's a small number, but there it is. Okay. So on a test, I'll show you. On a test, we've been sticking to throughout the course to just rounding off the 3 significant figures, so I just write it like that. Okay. So there is the force of static friction. sorry, the coefficient of static friction. It's a range. So um, to explain that, if you're less than this number, if mu(s) were less than this number, remember this is kind of a measure of how sticky the surfaces are or how rough they are, so that one thing can't slide across another. If it were less than that, then it would slide. Okay, and so it can't be less than that. It can be bigger than that. It could be like zero point 0.1, it could be 0.2, it could be 1, it could be 10, it could be a million. Okay, as long as it's bigger than this number, it's not going to slide. If it's less than that number, it will slide. Okay, so there's mu(s). All right. So let me see if there's any questions or any corrections if in case I made an error. In the meantime, I'm going to have a sip of coffee. All right, we're looking good. Okay, don't see any. Um, okay, so last question uh, is assume only the 9 kilogram has kinetic friction, and the kinetic friction is 0.03. Okay, now I don't remember if it was for your class or another class. I think it was another class. I accidentally made the mistake of making my mu k, because I hadn't solved the problem beforehand. I accidentally made the mistake of making my mu k smaller than mu(s). If that's the case, then the problem is wrong. Okay, then I made a mistake. Notice that mu k has to be less than mu(s). Why? Well, if it were bigger than mu(s), then it would slide, and then you wouldn't even be in a kinetic friction situation. You'd be in a static friction situation. So mu(s) is always bigger than, or at least equal to, that's the smallest it could be, is equal to mu k. So I know it's for the different masses, but even so, if I guess for the other mass it'd be slightly different number than this, but still, if mu k were less than, sorry, greater than mu(s), it will not slide. So mu k has to be less than mu(s). All right. So this time, just to change things up, I said, well, let's assume that it's the 9 kilogram that has the kinetic friction. All right, and this kinetic friction is that. This time, how much? How much kinetic friction is there, and in what direction? Now, for this problem, we do use this equation here. Sorry, this equation right here. Okay, not mu(s), but mu k. I'm just cutting and pasting because, okay, and divided by F2, whoops, equals like that. We are going to use this equation. So for the static, it's an inequality. As long as you're bigger than that minimum amount, you don't slide. For the kinetic, it's actually an equality. So once you have the normal force, okay, you can calculate the frictional force, okay, knowing mu k. All right. So well, we have F2 because F2 has got to counter the gravitational force. Let me show you that on the diagram. Okay, I'm going a bit faster than, like, not as much detail as we have before, because you've done a few of these now, and I kind of want you to see the flow more than just get stuck in the details. But I think you get the idea that this one, Fn2, has to counter that one. Okay, otherwise it'd be acceleration. All right, and so we have that the perpendicular gravitational force is m2g cosine theta, and that's got to be countered by Fn2. So Fn2 must equal that, and plugging in the numbers, I get that Fn2 must be 77.9 newtons. Okay, and now we can actually calculate Ff. Okay, Ff is going to equal, just rearranging this equation, multiplying both sides by Fn2, it's going to be mu k times Fn2 like that, and I give you mu k, there it is. All right, I give you mu k, and Fn2, normal force for mass 2, has to counter gravity, perpendicular gravity, and we know what that is. It's 77.9, like that. And that's got to equal, let me work that out. That's got to equal that number right there. That's how many newtons. Okay, so we have the force of gravity. Like here, it's kind of for static friction, it's kind of backwards. It's almost like you apply Newton's second law first, and then you work and you can get Fs. Here, you need F first, and then you can use Newton's second law to get the acceleration. All right, so we have that. Let's go back to the diagram and put those values in there. So let me see if I can erase stuff by just undoing, 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 undoing. Good. There we go. All right, so we're back to where we were before. We don't know FT, okay? Don't assume it's the same as before because situation has changed, okay? And we found that there is a frictional force now. It's what I say, 2.377. What direction does it have to be in? Well, we're looking at M2 here. M2 wants to slide downhill, and so the frictional force here has to be, let me do it in red, the frictional force here has to be uphill like that, okay? All right, so that's going to be FT. Oh, sorry, FF, okay? FF and FT, they're going to add together. They're both trying to slow down the acceleration downhill. Okay, they're both going to be competing against this one. Okay, which is the parallel component of gravity. Which one wins? This one does. So when you do F net now, it's going to be that value there, which we know is 50. I can actually write that back in there, like that. This value did not change from above. Okay, if you calculate m2g sine theta, it's still going to be 50 newtons here, and that's still 45 newtons there. Okay, that 50 newtons, that's competing against both ft and ff now. All right, so when we go back here, all right, so we're going to do that f net for number 2. What's that going to equal? Well, that's going to equal the 50 newtons. All right, so where did I get that 50 newtons? Well, way back up here where we calculated the right here, the parallel component of G, that doesn't change, okay? Just because whether it's moving or not moving, it doesn't matter. It's still 50 newtons. So that's where this 50 newtons came from here. This is going to be the parallel component of gravity, trying to pull it downhill. That's being competed with, or it's competing against Ft, the tension, but it's also competing against this one, okay? So everyone good? So this equation here for F net 2, that should look a lot like this one up here for F net 2. What's the difference? Well, in addition to Ft, you also have here that, okay? And what's that got to equal? Well, F net equals MA, and so that's got to equal M2 times A like that. And so this is going to reduce, let me do the 50 minus the, you know what, let me write it down first so that you can see what I'm doing here. So that's what I'm focusing on. Let's get rid of that newtons there. Okay, so I'm just going to subtract the 50 minus the 2.33 first. Okay, so 50 minus 2.337. All right, there's this minus Ft, and that's got to equal M2 is 10, 8 like that. There's our equation number 1 like that. Okay, and there's the analysis for M2. Okay, now I guess I started for M2, the 10 kilogram one, because that's the one that's more interesting. If you say, well, what if I do the analysis for M1? That's the 7 kilogram one. What's that analysis going to look like? And you can almost guess that nothing is going to change from here. Okay, all of this is exactly the same. Why? I guess we got to call it equation 2. Why is this all the same? Okay, why is that the same? We'll go back to the diagram here, and if you take a look at M1, well, there's no friction there. Okay, there's no friction, so you still only have Ft competing against that 45, which is winning the Ft. So F net is going to be Ft minus 45. Okay, so over here, so it's going to have Ft minus 45. That's your F net. So I guess up here, Ft minus 45. That's your F net. And because of Newton's second law, this equality right here, that equal sign, that's because of Newton's second law. This one is because of the vector sum, And this equality is because of Newton's second law. Okay, that's what justifies those equalities. And m1 is 7. Okay, so then you just get that equation right there. And now you basically have two equations, two unknowns again. All right, that one. And sorry, I guess I should solve 1 and 2. So there's 1. There's equation number 2 right underneath it. Let me just line them up like that. And actually, that's good enough. I think you can see what's going to happen here. If I add the 2, I add that side, plus I add that side. That is going to equal 17 times A, like that. Okay. And you'll notice that the FTs will cancel. All right, like that. And I'm going to get this value right here, 47.663 minus 45. It's going to be a really small number here like that. That's got to equal 17A. Okay. Divide both sides by 17. And I'm going to get divided by 17. I'm going to get this number. And again, rounding that off, 0.157 meters per second squared, like that. Okay, so that answers the second question. Does this make sense? Does that value make sense? Well, if you compare it to number 1, our first question, where we didn't have friction, you expect that, yeah, it's sliding, but it's going to be sliding slower than it did before. So if you take a look at what we got before, up here, we got that A was, so with friction, with kinetic friction, and this is with no friction. Okay, so it did work out. It doesn't work out. It does make sense. It does make sense. Okay, so again, it's good to make these checks because you make an error, and you'll when you go to do a redundant check like this, you'll see that there's some kind of a something wrong, and that will clue you into maybe you made some arithmetic error up above. Okay, now did I ask for the tension as well? What's the acceleration? You know what? What's the tension? All right. All right. So what's the tension? Well, again, to solve for Ft, sub into 1 or 2. Okay. And let's let's use this one. Let's use that one. That seems to be the easier of the two. Okay, so I got that, and that tells me that Ft is going to equal 7A plus 45, which is equal to 7 times A. We'll use that, plus 45, and that's going to equal that number there, which again, rounding off to 3 significant figures, is 46.1 newtons. Okay, and now this is with friction. Maybe it's useful to compare it to the previous one, and what do you expect? Smaller or bigger? And let's take a look here. What did we get up above for tension? We got 47 for tension up above. You expect it to be less. Okay, you say, well, why would I expect it to be less? Okay, this is without. That's because there's more acceleration, and so the 7 kilogram box has to be, something has to be pulling it uphill with more force because it's accelerating uphill more. Okay, and so there it is. All right, so it's 46.1 with friction and 47.1 without friction. Okay, so that answers that problem there. Okay, so that was all I was going to do. I guess I'm a little bit ahead of schedule. Let me see if there's any questions in the chat here. All right, was that fine? Did I go too fast over anything, or do you have any questions before we call it quits? I probably could have done a Newton's. That's okay. There's more than enough time. I was going to say I could do a universal gravitational law problem, but that's okay. I don't think it's necessary to overly squeeze things in. So I think this is fine then. Let's leave it there. And next time, as I said, what I'm going to do is I'm going to do basically Newton's gravitational law problem. Okay, so either one with the F is equal to capital G, that's universal gravitational law, m1 m2 over r squared. One of those, and or one with Kepler's third law. Kepler's first and second law, you just know them qualitatively. Kepler's third law you can actually use because that's the one that compares planetary orbits and planetary periods. Okay, and so that can be used to applied to like planets and say, well, you know how things like you know what the Earth's orbit is and you know what the Earth's period is around the sun, then you can calculate all the other planetary radii or orbital periods. And then we'll do another energy problem next time. Energy problems tend to be fairly easy, I think. If you've got them down conceptually, they tend to be fairly straightforward. All right, guys, I think that's it for today. Then I don't see any other questions in the chat. Let me just say goodbye, and we'll see you on Wednesday then. Unless you want to catch me during my office hours, I'm on every evening if you have any other questions. Okay? So, bye-bye.